Welcome to The Explainer. Today, we are cracking open one of the biggest secrets in AI. It's this tiny little on switch inside every artificial neuron. Now, it might just seem like a simple math trick, but trust me, it is the key that unlocks the incredible power of modern AI. Its ability to understand our messy, complicated world.
All right, so let's set the stage. Think about early AI, what we call symbolic AI. It was kind of like a chess grandmaster, right? It worked by following a huge, complicated set of pre-programmed rules. And for stuff with clear rules, it was a genius. But ask it to do something fuzzy like tell a cat from a dog? No way. It would just be completely lost. And that's where modern machine learning flips the script. Instead of feeding it rules, we just show it a ton of examples, and it figures out the patterns all by itself.
So that's a massive leap, right? Going from just following instructions to actually learning from experience. It begs the huge question, how in the world did we get a machine to perceive things? How does it actually learn to see or hear or even understand language?
Well, our best answer so far is something that's actually inspired by our very own brains. It's called the artificial neural network.
So here's what it looks like. You've got data, let's say the pixels of a picture, coming in on the left side, that's the input layer. Then it flows through these middle sections, the hidden layers. This is where all the magic, all the heavy lifting really happens. And then finally, it spits out an answer on the right, like, yep, that's a cat, or nope, definitely a dog. And that's the output layer.
Okay, so each one of those little circles in the diagram, that's an artificial neuron. The easiest way to think about it is like a tiny, tiny calculator. It gets a bunch of signals, and for each signal, it asks, how important is this one? That's the weight. It multiplies the signals by their weights, adds it all together, and then sends out one single signal of its own. Sounds simple, right? But here's the thing. When you chain together thousands or even millions of these simple calculators, that's when incredible things start to happen.
But there's a catch. A really big one, actually. Without one specific secret ingredient, this whole amazing, complex structure, it's shockingly limited. And this, right here, is the aha moment that really let deep learning take off.
So let's do a little thought experiment. What if we built this huge, deep neural network with all its fancy layers, but we forgot to add this one crucial part? What would actually happen?
Well, it would be a disaster. The whole thing would just collapse. Mathematically speaking, that whole deep network would basically become the same as one single simple linear model. And that means it could only learn straight lines. And let's be honest, the real world, with all its interesting, messy patterns, is definitely not a straight line.
And this is where our secret ingredient finally makes its entrance, the activation function. It's this little mathematical gate that sits inside every single neuron, and its job is to add non-linearity. You can think of it like a bouncer at a club. It decides if a neuron's signal is important enough to get through and fire. And it's this one simple step that lets the entire network start to learn the complex, curvy shapes of real-world data.
All right, but not all of these little gates are the same. So let's meet domain players, a few of the most important activation functions in the history of AI.
First up, we've got one of the OGs, the sigmoid function. You can see its classic S shape right here. What it does is simple, but super useful. It takes any number you throw at it, no matter how big or small, and squishes it down to a value somewhere between 0 and 1. And why is that great? Well, it's perfect for probabilities. You can get an output like, there's a 0.9 chance this is a cat.
But sigmoid has a pretty major flaw. See how the S-curve gets really flat at the top and the bottom? In those flat zones, the gradient, which is basically the signal the network uses to learn, gets incredibly tiny, almost zero. Now imagine you have a really deep network. As that tiny signal gets passed from layer to layer, it just gets smaller and smaller until it disappears completely. The learning just stops. This is the famous vanishing gradient problem, and it was a huge roadblock for a long time.
So that whole vanishing gradient issue led to a new hero entering the scene. This is the modern workhorse of most neural networks today, ReLU. That stands for Rectified Linear Unit, and its rule couldn't be simpler. If you give it a negative number, it spits out 0. If you give it a positive number, it just spits that same number right back out. That's it.
That simplicity makes it super fast, computationally cheap, and since the line just keeps going up for positive numbers, you don't have that vanishing gradient problem, at least on the positive side. But there's a catch here too. What happens if a neuron only ever gets negative inputs? It just outputs 0, over and over. It basically switches off and can sometimes never switch back on. We call these dying ReLUs, and they're neurons that have just stopped participating in the learning process.
Okay, our last main character is Tanh, which is short for hyperbolic tangent. Now, at first glance, it looks a lot like Sigmoid's S-curve, doesn't it? But look closely. There's a crucial difference. It's centered at 0. Instead of going from 0 to 1, it goes from -1 to +1.
And having that zero-centered output with both negative and positive values actually helps make the network's learning process a bit more stable and efficient. But you can see it right there on the graph. It has the same flat ends as Sigmoid. So yep, it also suffers from that same pesky vanishing gradient problem in really deep networks.
Putting these two side by side really tells the story, doesn't it? On the left, you've got Sigmoid's smooth S-curve that kind of gets saturated or stuck on the flat parts. And on the right, you have ReLU's sharp, simple, and super efficient line. This picture basically shows the entire field of AI shifting its strategy. We moved away from functions that could kill the learning signal towards ones that let it flow freely. And that shift is exactly what allowed us to build the incredibly deep, powerful networks that we see today.
So why are we getting so deep into the weeds on this? Does it really matter? Absolutely. In the real world, picking an activation function isn't just some abstract academic exercise. It's a critical decision that can literally be the difference between a groundbreaking AI model and a total failure.
And you can see it right here in the history of AI's biggest breakthroughs. Back in 2012, a model called AlexNet completely changed the game for computer vision. And guess what its secret sauce was? It was one of the first major models to successfully use ReLU. Then you jump forward to 2018 to BERT, Google's legendary language model. It used an even newer function called GLU, which is basically a smoother, fancier version of ReLU. The point is, the evolution of these functions goes hand in hand with the evolution of AI itself.
And when you get to the very last layer of your network, the output layer, the choice becomes really practical and depends on what you're trying to do. If you need a simple yes or no answer, like, is this email spam? Sigmoid is your go-to. If you need to pick one thing from a bunch of categories, like, is this a picture of a dog, a cat, or a bird, you use something called softmax. It gives you probabilities for each class that all add up to 1. And if you're trying to predict a number, like the future price of a stock or a house, you just use a simple linear function. No squashing needed.
You know, when you step back, all of these pieces we've talked about, the layers, the neurons, the weights, these activation functions, they all serve this one really beautiful and powerful idea. We've stopped trying to hand code rules for every little thing. Instead, we're just showing the computer a ton of examples and letting it figure out the patterns of the world for itself.
So if there's one thing to take away from all this, it's this. Activation functions are those tiny little non-linear switches. And while one switch doesn't do much, when you have millions of them all working together, they give the neural network this incredible, almost magical ability to learn pretty much any complex pattern you throw at it.
They really are the secret to learning complexity. And it kind of makes you wonder, doesn't it? Now that machines have really mastered this core building block of learning, what's next? What's the next complex, maybe even uniquely human trait that they're going to learn?